Welcome everyone. So today so just focus on the advanced function for the electrical probe station at NUFAB. I see some user already some familiar names in the audience, and I think you already know a little bit about our probe station, and probably already did some electrical measurement somewhere else. And today we will start from the basics and go to the advanced. So this is our probe station. It was upgraded about 1.5 years ago. So in this upgrade, we get rid of this old measurement equipment and brought in this KSAT B1500. This B1500 is quite a popular equipment for the semiconductor and the DC measurement at this moment. And I believe there are some other groups also have this equipment. And it's always looks the same because what you're looking at is just the mainframe. But inside this mainframe, there are many modules. So most of the B1500, as I know, just have standard SMUs, but for our case, we have more modules, something like SPGU and wave function generator. So those functions I will talk a little bit later. So according to the company, the KSAT, at the moment we upgrade this equipment, that's the first or the most advanced B1500 that is available in universities. So even after 1.5 years, I believe it's still very advanced equipment as you can find in the US. Okay, so we'll start with from the basic functions, and if you are a user of the probe station, you must already see something like this. So this is a sheet that we have always with the equipment, and it shows you the 4 most popular programs that users usually start with. So we will go through this one a little bit, and then we'll start from here talking about the advanced functions. So 2.IV, so it's the most popular one. So people use it to do a quick connection check, make sure something is conductive or something is not conductive at all. And also use for measure metals and make sure it has low resistivity, whatever. And sometimes people use it to measure IV curves, and those IV curves usually comes from a diode, dielectric, or something with nonlinear IV curves. So this is a major application of 2.IV, and 3.IV are used for measuring transistors. So transistors have 3 terminals: drain, source, and gate, and you're going to use a gate to control the source drain IV characteristics. And so CV is something to use to measure capacitors when you have a non-conductive material, which usually means it's a dielectric material. And capacitance character is a very important function parameter for characterizing a dielectric material, and CV is the most popular used characterized way to describe a dielectric material. 4.IV is relatively used less because it's not so straightforward. It's not just like you hook up the probes and run the program. It's a little bit further forward. So at this talk, we will start with this 4.IV. And this is the outline of this talk. So we'll talk a little bit about the 4.IV just to give you the background knowledge for you to use before you can come to do the measurement. And then the second is how to do the double loop for the 3.IV. And then we introduce a little bit pulse into the IV functions. And then above that, we can apply arbitrary waveform. And if you need very high-speed measurement, we will also talk about how to do that measurement. And one more thing, the last thing is RF probes, which is a necessary accessory for doing the short pulse and high-speed measurement. Okay, so 4-point IV. So why do you need to use 4-point IV? So the reason is you want to eliminate the contact and wire resistance from the measurement. So contact, everything when you make a contact, there's a resistance at the contact point. And when you lead the current or voltage to the device, and the 2-point IV always include the wire resistance from the cables. But many cases that you want to know just the intrinsic resistance from the device itself. You don't want to know what is the resistance over here. You don't want to know the resistance over here. If you want to know the precise resistance, and you want to use that number to calculate the resistivity of this material itself, this is 4-point IV that you must use. One application case is to measure sheet resistance. For example, if you deposit a film, no matter which kind of film, or you dope a silicon wafer, and you need to know what is sheet resistance. So it's from the sheet resistance, then you can calculate the resistivity, which is the intrinsic property related to the material itself. So this diagram, we have it with the equipment all the time, and it shows you quickly about how to connect the probes and how you load the program and how you run it. But before you come into the electric probe station and setting up the probes, then what you should know is you need some background knowledge. So here I give a very standard way, or we say a mostly used way to perform the 4-point IV. So this is about how you connect the probes for the sheet resistance measurement. And so as you know, we're gonna have 4 probes. The outer 2 gonna apply a current, and the inner 2 gonna measure the voltage. Something else you need to know is that these 4 probes, the 1, 2, 3, 4 probes should be aligned in a single line. It should be strictly aligned, and the distance between the 4 points should be the same. So that's a requirement for you to use this simple calculation to get a sheet resistance and therefore calculate the resistivity. And there's further assumptions for you using this geometry is first, the thickness of the film is much smaller than the width or the implant diameter, implant dimensions of the film. And also the distance between the probes is much smaller than the film dimensions. So this is the assumption built on to let you use this sheet resistance calculation. If your sample and your connection can fulfill that requirement, then you're gonna put the probes there, and then you set up the program, and then you run it. Then this software will give you a curve, an IV curve. Mostly it's a straight line. And then you use a delta V divided by I, and then it can calculate resistance. You multiply a simple factor, and that's your sheet resistance. If you know the thickness of the film, then you can directly convert it to resistivity. So this is the most important factors that you want to get with this 4-point IV. This measurement is usually required if you have a very low resistance material, especially some metals, because in that case, the resistance from the device of material itself is usually much smaller than the contact resistance and the wire cable resistance. So yeah, the 4-point IV is for precise resistance characterization. Now we talk about the double looped. So when we do the training for the perf station, what we always start with is we ask you what kind of measurement you want to use and what kind of device you have. So we'll start from there. And then usually the training will fall into the categories of those basic programs. So many people also ask, like, can you go one step deeper to introduce the software? So this is also the chance that I can show you that's how the software is built if you want to know more than just you need. I use this double loop 3-point transistor as an example. So first, for the 3-point IV and the program we gave you here is for a single curve. So you can fix a gate and measure the IV over the source and drain, or you can fix the source drain voltage, measure the gate and the source gate and the current. So no matter what, you only get one curve after running this program. But usually when you characterize a transistor, you can see something they saying this type of curves is required, which means you need to have a bunch of curves. And if you don't want to measure one by one, so this is a solution where you go to automate this 3-point IV and measure the bunch of curves in one sequence, and it switches automatically from one to another. Okay, so what we going how to use it is that, again, we have the software open here. Instead of loading programs like this way, you go to the application test. And from here, you have a category. And the category is a lot of device names, something like BGT by some like diode and CMOS, some memory, all those kind of device. So today I'm going to select the CMOS for the transistor IV. And under it, there's a library associated with this CMOS device. So this is common programs to characterize the CMOS. Actually, KSAT and Easy Expert are doing a very good job that to supply all kinds of programs that they can think of, and they already built the programs and load it into the software. So I'll say 99% of your needs will be able to find into the application test. So it's if you want to explore, so this is something that go to application test, select the device type and see what kind of program they have. So today I'm going to select the CMOS and then select IDVD and then just click on it. It will bring you up to this kind of a diagram. It's very intuitive diagram and it tells you, okay, so this is how the device looks like. And you have a primary sweep and a secondary sweep, so which means double loop. So you have a SMU. So this one you can select which probe you connect to the drain and which probe you connect to the source and which probe connect to the gate. So with the prime sweep, you first do the IV of drain and source, and then you jump to a second sweep, change the gate, and then do this sweep again. So after this program, you're gonna have this type of curves plotted out. And for each parameters, it's also very intuitive. I have a start and stop and step. So yeah, this is simple programs that you can explore by yourself in the application tests. The next is so IV that we want to have a little bit fancy over the IV. So something like you can apply a pulse. So again, I put out this basic 2-point IV here. So in the channel setup, and we usually select the current or voltage, but if you open the list, you have pulse current or pulse voltage. So pulse voltage is used when the sample a device can generate a lot of heat when you can apply a continuous current or voltage. So the pulse is used to avoid self-heating and also minimize trapped charges, especially when the device is coupled with any dielectric, any capacitors. Yeah, so this is a pulse. So very simple. Instead of selecting the voltage, you select the pulse voltage. And when you go to the next step, the measurement, then you will have this little window in addition to whatever you see before. And this is one you can control the pulse. So you can control the width of the pulse and you can control the base, which like a pulse and build on top of something. And when you can put whatever number you want, and when you hit on the range of if a setting is out of the range of the allowed, then it will give you the message telling you what's allowed range for those parameters. And so for here, the minimum width of this pulse is 500 microseconds, which is 0.5 milliseconds. And that is whatever the standard SMU can supply for the pulse. Yeah, and if this pulse looks too long for you, then we still have some solutions to give you a shorter pulse, which comes to the SPGU, which is called semiconductor pulse generator. So this pulse generator is pretty powerful, and it can go to the width down to the 10 nanoseconds. So this is the smallest pulse that we can ever get from the market and existing equipment. So this is the lowest value that we can ever search for. So to use this one, again, we still start with this 2-point IV program. So you will see we have a add SPGU button here. You click on it, it's gonna give you an additional row. And this one is default with the unit name and also default with the pulse. It's on the voltage. It's not gonna be on the current. So it's just very simple that you can add this SPGU into your program if you need a very short pulse. So again, when you go to the measurement tab to program this SPGU, you will have this kind of page to allow you set up this SPGU, which also how the pulse looks like. And this is also, again, very intuitive. You should be able to read from the name. It's like what's the period of the pulse and how many runs you want to have and how many taps, how many pulses you want. And again, so like what's the base voltage, what's the peak voltage, and what's the delay between each, okay, the delay is something else. What's the width of the top peak and leading the ramping up slope time and ramping down slope time for the trailing. So this is all the parameters that you need to define a pulse. And these parameters can go, especially the time, can go all the way down to 10 nanoseconds. So this one also gave you more flexible settings because you can define the leading and the trailing time instead of just how long the pulse is and how high the peak is. So instead of 2 levels, you can have 3 levels, which is the 1 pulse up and the 1 pulse down. So this SPGU give you more flexibility. Basically, you can program all the parameters for pulse. The only thing that to keep in mind that this SPGU is only apply a pulse. It doesn't do any measurement. So other units like SMU, that means you can do the measurement, but this SPGU, you can only supply a pulse. And then when you do the IV program, so you use this one, and then the measurement job will be laid on to the other SMU. So you're not going to read anything from here. So the reading parameter will be associated with this one. But this detail set we can always discuss when you really want to use the program. I'll give you an application example for here is some high electron mobility transistors. And I believe these transistors is already exist in many labs. So if you want something to challenge your device a little bit, go a shorter pause and talk to us about the option using the SPGU. Okay. So from SPGU, so you have a lot of flexibility to define the shapes of this pulse, but still it's gonna be a pulse shape. But if you want any arbitrary waveform, like you want to simulate any some certain external conditions, so which not necessary to be a pure pulse, then you can go to arbitrary linear waveform generator. And again, so start with 2-point IV, and when you add SPGU, you have this SPGU row. Instead of going to the V pulse, you can select the ALWGU. And then in the measurement tab again, it will give you this option, a window to set up this arbitrary waveform. And this is how you're gonna edit a waveform. So it's very simple table. As so the voltage as a function of the time, so you can define each point on the waveform, and it will just give you arbitrary waveform as you want. Okay. So far we still talking about adding pulse, adding arbitrary waveforms into the IV curves. This is just add a pulse or add additional voltage to the measurement, but again, this one doesn't measure as you apply. If you want to measure with in the meantime, as you apply a very short pulse, then you should consider another function, which is another unit. It's called a arbitrary linear wave function and fast measurement unit. So it's pretty long name now. So the advantage of this one is again, so as I said before, so it can supply a voltage and measure the current at very fast speed. The speed can be down to nanoseconds. So you can get 1 point every nanoseconds. So I'm not going to go deep into how you're going to use this unit because it's a little bit complicated and I don't think I can cover it here. I just give an introduction here. So this is, again, we go to use this one. We go to application test and go to this FG, WGFMU, and then there is some pattern generator. And you just simply click on this button and then you will be able to edit the waveform and enter the parameter for the measurement. And so here is an example that we used this unit to do the measurement we did on a resistor. So this is as a function of the time. So you see this big grid is 100 nanoseconds, and the blue one is the voltage applied. So it's measuring the voltage as it applies. And in another unit, we have it's watching the current. So it measures the current as a voltage applied. So it's basically the device's response to this very short pulse. And you can see we have a really nice dense curve with enough points and a very short pulse, everything. So yeah, this one can go to really fast speed and with nanoseconds time spacing and also apply a very short pulse. Okay, so we talk about a lot of functions, talking about challenging the time limit and how to go to very short time and in the programs and how to do the measurement. But if you want to do the fast or short pulse, there's one accessory that you must use, which is RF probes. So RF probes is additional 2 probes instead of the common probes that you see usually. So this probe, so why do you need to use it? Because we're applying a DC voltage here. It's like a square wave function. And you know the square wave function is not really a square wave. So it's actually built up by a lot of sine wave functions. So once you program this square, and the software will convert it to how many and what kind of sine waves that it need to build up together, and eventually the voltages will add up to this kind of square wave. And in these sine waves, there can be many comes with a very, very high frequency, up to tens of gigahertz. So you must make sure that you can transmit all those waves. No matter how high the frequency is, you want to transmit it into the device. You don't want any wave lost in the cable or in the connections. So this is where we're going to use the RF probes to give a really good shielding for the cables and also the devices, so that all the sound waves can be passed nicely to the device. And this is an example, like if you have a nice, so you program like this way, and you can pass all the wave functions over the sine functions over there, you're gonna have a clean and nice square wave. But if you lose some of them, and you easily can get this kind of oscillations at the end or at the beginning of this square wave. So this is caused by a poor shielding that when you use without these RF probes. Okay, and this is just like you need to use it and how to use it. So this is a picture of these RF probes coupled with our probe station. So usually you don't see something like this because first it's very dedicated, and then second it takes a lot of space. We usually don't put it on the probe station and keep it somewhere safe. But this is how it looks like when it's coupled with the probe station. So we have 2 big chunk of positioners, and the positioners will lead you all the way down to the very small tip. And this positioners comes with 2 separated cables instead of those kind of ones. So this blue SMA cable that's used to pass the RF signals. And these cables will connect it to somewhere else. But if you want, the probe itself is very, very small over here. And to get a close look, so this is what it looks like under the microscope. So each probe have 3 pins, and the 3 pins will all touch onto your device. So this is a device that we get from a resistive memory device, which basically you can consider is like a resistor. So the resistor is over here, and all around is the shielding. So for these probes, we have 3 pins. Only the middle one is passing. The middle 2 ones are passing the signals. One is apply voltage, another measures current, and the outer 2 are for the shielding. And the thing is that when you use these probes, the 2 probes must be opposite to each other in a 190-degree orientation. And also the distance between the pins are fixed. It's not flexible. And your device must be able to go with these pins. So which means that before you pattern the device, you need to think about whether you need to use it after RF probe or not. If you need it, make sure that your device are patterned in the geometry that can match the RF probe geometry. So just here for your information that the distance between these pins are 150 micrometer. Yeah, so this is RF probes that to use when you need to have a short pulse or do the fast measurement. I have introduced a lot of advanced functions here. I dumped a lot of information to you. So now it's time we can have a little bit summary. So first we did how to measure precise intrinsic resistivity of a low resistor. And second is I showed you how to use the software and looking for some programs. And the example is how to automate the 3-point IV that you can use measure several curves in a single program. And the third is you can introduce a little pulse. Instead of applying continuous pulse, you can introduce applying continuous voltage, you can introduce pulses to the IV measurement if your sample have strong heating or a capacitor. And if you want to reduce the pulse width, and if you can go to the short pulse function, and if you want to measure very fast as you have a very short pulse, then you can consider the fast measurement. And when you do that, advanced functions, always keep in mind that you may probably need to use RF probes. And using the RF probes, we need your device geometry matching the probe geometry. So this is a lot of information, but we just want to give you the idea that we have the function. You don't need to know exactly at this moment. You don't need to know exactly how to use it and where to find the programs. All those things you just leave to us. So you tell us all you need to do is think about it, whether these functions will be useful to you, and be brave to exploit by yourself. And if you have any questions or you need anything to any hand holding, just contact me, or you can just simply send, if you can't remember my email, just send the email to our general contact email, which is nufab@northwestern.edu.